Welcome back. In the last video, we defined normed linear spaces and bounded linear transformations on those spaces. There was one theorem we discussed and we proved, and this is the one currently displayed. Now, we will now continue here, but let me make one more comment about the theorem. So if you think back to a class, say in calculus, if you look at linear maps, or more generally continuous maps on the real line, then you know that they map compact sets to compact sets, right? And if you were on the real line, then of course a closed and bounded set, such as say unit interval from -1, 1, would be compact, so a function, a continuous function on that set would necessarily be bounded, right? So that being said, you can now see a clear difference here between these finite dimensional spaces, say here R1, and here in general infinite dimensional spaces, because a priori that closed ball, though bounded and closed, is in general not compact. So in general, continuous functions or normed linear spaces, they need not satisfy this property by default, right? You have it when you have the linearity and at least one of the other properties, but just continuity itself won't give you number 4 here for free, okay? So let's keep this in mind, because the theorem that I would like to discuss now in this lecture actually builds on this, okay? This is our second theorem. It is a bit more difficult to prove than the last one. The last one was, well, exploiting the linearity of the transformation and the normed linear space throughout. Now this one is a little bit harder. It's called the equivalent norm theorem, okay? It has several parts to it. Now the first one, this is a generalization of the classical Heine-Borel theorem. So the Heine-Borel theorem says that if you have closed and bounded sets in Rn or Cn, so finite dimensional coordinate spaces, then those are compact. And that is actually if and only if, okay? Now here the first part is a generalization of that statement, in that it says a normed linear space is finite dimensional if and only if every closed and bounded subset of it is compact. Okay, so remember how compactness was defined in general metric spaces with the open cover property. Okay, that's the first part of the theorem. Now the second part is, suppose you have a finite dimensional space, then number 1, that space is always gonna be complete, right? So completeness means you take an arbitrary Cauchy sequence and then it will be convergent in the space. Moreover, this is quite cute, this is very useful in applications. If you have, say, 2 norms on a finite dimensional space, then they are always what we say equivalent. Okay, what does that mean? Well, you can find constants C and D such that you have this double inequality in place. Okay, and why do we say they are equivalent? Well, look, if you have, for instance, a sequence which is convergent here in the first norm, then by this inequality automatically you would get the convergence in the second norm for free, and vice versa. If you have a sequence which is convergent in the 2 norm here, then you take the lower inequality and you get for free the convergence in the 1 norm, right? So that's why equivalent, because both norms induce the same notions and types of convergence. Okay, so that's what we'll have. Okay, now this theorem, it will take a little bit longer to prove, and in fact before we start proving those 3 properties, we will assemble some general facts that will help us eventually in proving those 3 properties. Okay, so let's get started. General, if X is finite dimensional, okay, this is a notion that is defined in linear algebra in terms of a basis that has only finitely many elements, and then if you have this, there's a unique number attached to that space, which is the dimension. Let's call it n, and as I already said, basis, so finite dimensional vector spaces have basis, This is a constructive proof in linear algebra. What allows you the basis to do? Well, it allows you to expand any vector in terms of that basis, right? So then for any x in x, we have that x is a linear combination of the basis elements. There are some scalars, alpha sub j here out front, for some alpha j, actually unique. Okay, if you have a fixed basis, then these alpha j's are always unique. This is because the elements in the basis have to be linearly independent. Okay, so we have this. Now let's assemble some general facts here. In turn, so we have the triangle inequality in X, because X is a non-linear space, right? This is the general assumption here. If X is a finite dimensional non-linear space, in turn, by the triangle inequality on X, we have, so I have this now here, and for the moment this can be any norm on X. So I have this. Now triangle inequality tells me how I can estimate those sums. So this will be sum of alpha j x j. Then the norm is homogeneous, so you can pull out the scalar factor in a complex modulus or absolute value, depending on what the underlying scalar field is. Okay, and now what can you do next? Well, I claim this you can estimate by c times j1 alpha j. And what's the c? Well, you got finitely many real numbers here, namely those lengths of xj. Well, you take the largest one, right? So maximum xj and j from 1 to n. Okay, if you take the largest one, then that c won't depend on the summation index. You can pull it out. So you're at this stage, and now what you can do is you can realize that this sum is precisely alpha j times 1. So you can apply the ordinary Cauchy-Schwarz inequality that is proven in linear algebra when you discuss inner product spaces. So here you take the inner product space Rn. This has a naturally associated inner product, so you have the Cauchy-Schwarz inequality, right? So you do this here. Here's the first factor and here's the second factor. Now Cauchy-Schwarz will tell you that, okay, the c you just copy, and then you have square root of the sum j1 up to n, and then 1 squared. Yeah, that's just n and then a square root, so you got square root n. And then the one which is left, you just write as is. So alpha j squared and square root. Okay, that's what you have. Okay, that's the first observation. So what does it mean? What do you deduce from this? So the map, let's define it, T from the coordinates alpha 1 up to alpha n to that linear combination j alpha j xj. So this is a map from coordinate space Fn into your finite dimensional normed linear space X. Okay, so what does that little estimate on the previous page tell me? Well, first of all, it is a linear map. This is clear from linear algebra, how you manipulate finite sums. Okay, it is linear, it is bijective. Why is that? So bijective requires two properties, surjectivity and injectivity. So why is it surjective? Well, because any vector x in here, small x, can be expanded in this form because the xj's form a basis. So that gives you surjectivity. And injectivity, well, this is actually the linear independence, right? So if such a sum is equal to 0, since the xj's are linearly independent because they form a basis in particular, all the alpha j's have to be equal to 0. So that gives you the injectivity. So together you got bijectivity. And what does the estimate on the previous slide tell us? Well, it's a bounded map, okay? Provided, well, a bounded linear transformation, but then I have to equip my coordinate space with a norm, right? So let's do this. Fn, I will write subscript E for Euclidean, is equipped with the Euclidean norm. So the Euclidean norm is just the ordinary sums of squares of the coordinate thing, and then you take a square root at the end of the day, right? So let's write it out. If you have an n-dimensional vector in the coordinate space, the Euclidean norm, as I was just saying, is sums of coordinates, well, in complex modulus square, and then a square root, right? So, and then why is it bounded? Well, because this last estimate here, you have t of x right here, and what we showed is that the norm of t of x is less than or equal to constant square root n, and then alpha 1, alpha n in Euclidean norm, right? That's precisely the boundedness of the map T. Okay, good. That's the first observation. Also, next, note, we will use all those observations later when we actually prove the theorem. Next, note that the norm itself, so the function which assigns to a vector its norm, is continuous. This is a continuous function. Why is this? Well, because of the triangle inequality. But this time I don't mean the triangle inequality upward, I mean the lower one, okay? So that is a cute exercise. You can show that the, yeah, maybe I will write the upper also. So this one here, this is by definition of a norm, because you have the triangle inequality. But then the triangle inequality, since it has to hold for all x and y, you can easily convince yourself it has to satisfy the lower one as well. How do you do this? Well, you write x as x minus y plus y, and then you use here the ordinary triangle inequality, like this, and then you can bring this quantity to the left, and then you have length of x minus length of y is at most, well, the length of x minus y, but then you just flip the roles of x and y, and that's how you get here the absolute value. Okay, yeah, but this here tells you precisely that this function f is actually not just continuous, it's Lipschitz continuous. Okay, so you have this. Okay, so why do I need this? Well, because I already have a continuous linear transformation T. If I now compose it with another continuous function, that composition will be continuous. That's a property in metric space theory. Okay, composition of continuous maps are continuous. Okay, next node is continuous. So the composition F circle T, which is a map from Fn into the non-negative real numbers, because T maps Fn to the vector space X, and then F takes that to non-negative real numbers, is continuous, well, everywhere on X. So in particular on the sphere, here's another notation that I tend to use. So the partial in front is the boundary of the open sphere. So here by definition these are all n-dimensional vectors alpha whose Euclidean length or norm is equal to 1. Okay, this is continuous as composition of continuous functions, and the sphere is compact by the Heine-Borel theorem. Okay, I mentioned this earlier. If you are in coordinate spaces Rn or Cn, so n-fold Cartesian product of the real line or the complex plane, then sets are compact if and only if bounded and closed. Okay, and you can convince yourself easily that this sphere is bounded and closed, so it is compact by Heine-Borel theorem. Yeah, but if you now have continuous functions on compact sets, they have extreme values by Weierstrass theorem. Okay, so that's what I'm going to use. Thus, there exists beta on the boundary so that, well, it is a minimum, say. It also has maximum, but I also only need the minimum. So that this is true for all alpha dB1. Okay, but f of t beta, so what is this? Let's write it out. So f is just the length of t beta, and now what does t beta do? Well, it's written out there, so it takes up here, so it takes a coordinate vector to this linear combination, right? So this would be something of this type, where the beta j's are the coordinates of the vector beta in Fn. Okay, so but we claim that this is of course positive. And why is this? Well, because if it were 0 by the norm properties, that can only happen if that whole thing inside here is equal to 0, but xj is the basis, so that will only happen when all the beta j's are equal to 0, but this can't be, because beta is chosen from the boundary of the unit ball, right? So it has to have length equal 1. It can't be the 0 vector. Okay, so we have this, and now if you combine this, hence, thus, so f t alpha is t alpha, and this is at least, well, ft beta, which is positive, right? So this is some constant c, and now I'm gonna do here a little bit of a trickery. I'm gonna write here the length or the norm of alpha in the Euclidean sense, but this is of course 1, so I can always multiply here by 1, but you will see later why I prefer this. Okay, so this is positive for all alpha in dB1. Okay, good. So if you have this, you should read this here and this here. Then of course, if this is true for all alpha, remember t is bijective, so it has an inverse. Now you can replace just alpha by t minus 1 of, well, the pre-image, right? So in particular, hence in particular, we have the inverse e less than or equal constant d of x for all x in x. Okay, so this really follows from the last inequality. You replace alpha by t minus 1 of x. Okay, so you have this, and this in particular shows, of course, that the inverse of t, remember t is bijective, is also bounded. Okay, good. So these are all the observations that we need to now finally prove the theorem. So there are 3 parts to it, right? So we will first begin with the completeness. So first one, let yk be arbitrary Cauchy sequence, so I have to show that it's convergent, right? Be Cauchy. Well, since these are vectors, so the sequence, each term is a vector in a finite dimensional space. That means each term can be written in terms of the basis, right? So it has coordinates, be Cauchy, with coordinates alpha k. So this is a sequence in Fn. Okay, so each alpha k is an n-dimensional vector, meaning, let's write this out. So alpha k, say, is an alpha k1, alpha kn in Fn with yk is j1n alpha kj xj. That's what I mean by coordinates. Okay, then by the above, so I want to say something about alpha m minus alpha k. So those are the coordinates. Then these are just the pre-images. This is how T is constructed of ym minus yk e. But you can still see this up here. You have this inequality. So use it. Less than or equal to d ym minus yk. Yeah, but ym, that was the Cauchy one, so this inequality tells you that the coordinates are also Cauchy sequence, right? So alpha k Fn is Cauchy. Yeah, but our scalar field is either the real numbers or the complex numbers, and then the n-fold copy thereof is of course complete because the real and the complex numbers are complete, right? So we have this is Cauchy and thus convergent. Okay, say to some, call it alpha star 1, alpha star n in Fn. Okay, good. In turn, by our first inequality that we wrote down in this proof, this was, we used the triangle inequality and then the ordinary Cauchy-Schwarz inequality. So if you follow those steps, you will find out there was this constant capital C, then there was a square root n, and then there was the Euclidean norm of the coordinates. So here you just use this inequality for this difference. Okay, so you have this. Yeah, but as k goes to infinity, since alpha k is convergent to the alpha star, this difference will become small. N is finite and does not go off to infinity. As k goes to infinity, this goes to 0. And this simply means that the sequence yk is convergent. So yk is convergent. And well, here's the limit of it, and this is clearly an element in X. So that's why the space is complete. Okay, that was property number 1. Property number 2 is actually now super easy with our work up front. This is about the equivalent norms. Well, since our above estimates hold for any norms, so when I started estimating, it didn't matter at all what kind of norm we put on it, so I can now do it for the 1 norm and for the 2 norm. We find at once so the first one was, this was really, I do the 1 norm is less than or equals c square root n, then the coordinates in the Euclidean norm. Yeah, but the coordinates in the Euclidean norm, this was the pre-image of t under x. So you have this. Okay, but then here for this guy here again, you use our box up there with the 2 norm now in place, because remember it worked for all norms. So Cn, then there's a d x2, and now again sort of you are here and then you do the same thing that you did from the left, just replace 1 by 2. Okay, so you continue this inequality, and out comes, if you read carefully the factors, c square nd t minus 1xe, and then you apply the yellow box again. Constants start piling up in front, but at the end, you know, you get what you want. Okay, so now you started with one norm of x, in the middle there was a two norm of x with a constant out front, and now you ended up again with the one norm in x with another constant out front, and that's precisely the equivalence of norms. Okay, good. Finally, the last property is about finite dimensional if and only if closed and bounded sets are compact, right? So of course, if you start with a compact set, that's always going to be bounded and closed. This has nothing to do with the dimension of the space. So this is clear. So we only have to do the other way around. So assuming every bounded and closed set is compact, we now show that the space has to be finite dimensional. Okay, so if every bounded closed set is compact, then the closed unit ball has to be compact. Okay, so in particular, totally bounded. Okay, actually thinking about it now, I'm already exceeding the 25-minute mark. I don't want to go much longer than this, so I will rather postpone completing this proof to the next video. Okay, so we still need to do the third property, assuming bounded closed sets are always compact. I will deduce that the space is actually finite dimensional. Okay, see you soon.